So here's the plan, at least tentatively, assuming that there's no snow day on Friday. So we're gonna do a little bit more in 5.3 today, and we're gonna do 5.4. I'm not gonna ask you to do more quizzes on the same day you're taking the related rates test, because while I'm crazy, I'm not that crazy, right? So we'll plan on doing the 5.3 and 5.4 homework quizzes Tuesday of next week. If there is a snow day on Friday, that would be your snow day assignment. I would just assign you to do the 5.3 and 5.4 homework quiz on the snow day, because I don't want to cover anything new at that point, especially with the related rates thing coming the next class period. Does that feel doable? So we'll do the related rates Friday or the next class period if there's a snow day. Would you rather do that the first half of the class or the second half? First half. I think that's for the best. That's what second hour wanted to do also. You guys remember the format?
Yeah, multiple choice from
5 multiple choice, and then 3 free responses. You pick 2 to do, right? 10 points for the total on the multiple choice, and 10 points each free response. If you divide that evenly, that's like 15 minutes on the free or the multiple choice. So like 3 minutes a question, and then 15 per free response question, which should be plenty of time, even if you're a little, takes you some time to process things. That's a lot for one of those free responses. 15 minutes is a pretty good chunk of time. Where would the multiple choice questions be coming from? Sets 1 and 2, similar to those, and then the free responses are going to be more like sets 3 and 4. The scenarios will be familiar, right? So like the problems are going to sound like the problems you've done already. I didn't cook up any like brand new thing that you haven't heard about before. It'll be familiar scenarios, as I think I've given you between these 4 sets, all of the most common, kind of questions that you might run into. Do you guys feel okay about the related rates thing? The second half of class, then that day we're going to look at section 5.5. So the next week we'll take like a review day to kind of take some of these homework quizzes, get settled, do some review stuff, and then we'll be looking at our, like chapter test, probably, or unit test at the end of that week, the end of next week, or if there's a snow day, the start of the week after. Right? And that's all this soft schedule. We're going to see how things, after we get a chance to start putting this all together, how you guys are feeling, and talk about test format and that kind of thing. But is that okay? Giving you a heads up as to like what's coming down the pipe here. Do you guys have questions for me about the schedule or anything that's happening soon? Perfect. So today I'm going to start. We're going to do some like AP style free response questions that are kind of centered on the content from 5.3 and then might include previous ideas. But the key idea is going to be these fundamental theorem of calculus concepts. And then we'll do 2 or 3 of those, and then we'll transition into 5.4, which should not be a difficult section. It should be like, yeah, this is what I'm talking about. Section. Okey-doke? Let's get us started. So Here we're told the graph of some function f is shown above, and it consists of two line segments. And g is this like accumulation function, right? It's this integral function, like area so far function. We're asked to find g of -1, g prime of -1, and g double prime of -1. Everybody feel okay on the setup here? So if I want g prime of -1, I'll just plug -1 into my function for g. Now, if I look at that integral, that looks a little funny to me, because the lower bound is 0 and the upper bound is -1, right? We've defined these accumulations as going from like to the left to the right, not from the right to the left. So the first thing that I would want to do is to switch those bounds so that it's going from small to big. Now, do you guys remember we had a property that allows us to do that, but in doing so, it picks up a negative sign. Right, but here we went big to small, right? We want to go from small to big. Yes, that is what we're looking to do. Is that okay? And so we're talking then about like that area, right? Because an integral is the same as the area under a curve. And that area is just a geometric shape. It is a triangle. To find the area of a triangle, I do 1/2 base times height. The base here is 1, and the height is 3. So this should be -3 then, right? Why is the negative? That we picked up from swapping the bounds. Oh, sure. 3/2. Thanks. Thank you. Does everybody feel okay there? Okay. So now let's look at g prime of 1. Well, I know that g of x is this, right? If I want g prime of x, I'll just do the derivative to both sides. What's the derivative of that integral? F of x, right? So if I want g prime then of -1, that's the same thing as f of -1, which is, no, 0, right? Just that point. Everybody feel okay there? Okay. And now if I want to talk about g double prime, well, I know this. If I want the double prime, we'll again just take the derivative of both sides. Okay there? So if I plug -1 in, what's f prime of -1 mean? The slope of f at -1. Notice that at -1, f is a straight line. So I can literally just calculate the slope, right, of that line segment. So this is like 0, 3, and that's -2, -3. So we get 6/2. Does everybody feel okay here as we're looking at the relationship between G prime, and G double prime, fluid integral of F, and F prime? See the relationships here? So be common problem formulation, common problem setup on the AP exam. Okay. Part B says, for what values of x in the open interval -2 to 2 is G increasing? What does G increasing mean? How would I check for that using calculus? If the derivative is positive. That's correct. And G prime was the same thing as f of x, remember? Now, why am I wanting to translate this into f of x? Do I have a graph of G? Do I have a function that I can easily evaluate for G? Not really. Do I have f? I know lots about f, right? I'd much rather talk about f than G. So I'm just looking at where f is positive. Where is f positive? -1 to 1. Because that's where f is above the x-axis. Does that feel okay? Okay. Part C says, for what values of x on the open interval -2 to 2 is the graph of G concave down? What does concave down again mean? Second derivative is negative. And G double prime is the same as F prime. And where is F prime negative? Where F slope is negative, which starts at 0 and ends at 2. Is everybody okay with what I'm doing here? Notice that computationally, none of this is complicated, right? But you have to understand what you're looking at. You have to understand the interplay between the integral and the graph, and how to use the graph to answer questions about the integral, right? Is this feeling okay, though? All right. On the axis provided, sketch the graph of G on the closed interval -2 to 2. So when it says sketch the graph, really what that means is the y-axis really isn't important. So I'm not going to really bother adding any labels there. Okay, so in summary, what do I know? I know g of x is increasing from -1 to 1, which means that it should be decreasing elsewhere, right? That it's concave up, down from 0 to 2, which means that it should be concave up everywhere else, right? Okay. So I'm going to start my graph of G, and I'm just going to be like
I don't know, start it here maybe. And then I'm decreasing all the way to 1 and concave up at that time. So it's going to look like that. At -1, oops, that should be -1. We switch and become increasing, but we're still concave up all the way to 0. At 0, we switch to concave down, but we're still increasing. At 1, we stop increasing, and we change to decreasing, but we're still concave down. So we're going to look something like that. Okay with how I kind of sketched in that picture? Now, from what we used here, is there any way to tell how high or low these humps should be? Where these y coordinates are located, whether they're above or below the x-axis? No. Now, we could do that. We could calculate some specific values for g. And I suppose that we should have probably included that g of -1 was -3/2, right? So I didn't do that. So here would be what I would do to fix it. Not changing my picture. Just going to move the x-axis so that that spot is where I want it to be. Right? This is me being clever. Like, oh, the shape is fine, it's just the x-axis is in the wrong spot. Let me just move the x-axis. That's a lot easier than redrawing this graph that took me, spent 2 minutes thinking kind of hard about what this thing was going to look like. I don't want to have to redo that. Questions on what I did to here? Notice there's a lot of first and second derivative information from first semester involved in this, right? This is going to be very common as we go on. We're going to start stacking ideas on top of ideas. We're going to take first semester ideas and stack them on top of second semester stuff. Very common. AP loves to do this. And layer ideas one on top of the other. Let's do another example. Fairly similar presentation. So you're given some piecewise function f, no formula provided. And we're asked to, and given some function g that's based on the integral of f, and asked to do some analysis, right? So it says, does G have a relative minimum, relative maximum, or neither at x equals 10? Justify your answer. So what do I need to do to check to see if G has a maximum or minimum? I need to look at the critical values of G, right? What are the critical values again? Everybody's okay there? So what's the derivative of G equal to? F of x, right? Here's my graph of f of x. Is f of x undefined anywhere? Nope. So that's gone. Where's f of x equal to 0? Okay. So -2, +2, 6, and 10. Now, just because 10 is a critical point, does that guarantee that it's a maximum or minimum? No, right? What should we do to accompany our critical point? How do we check to see if it's either a maximum or a minimum or neither? We should do either a first or second derivative test. My opinion here is I would do a first derivative test. So to do that, I'm basically going to just make a sign diagram. I'll pick some values on either side of 10, but are still like in between the next critical point. So really anything, between 10 and 12 would be sufficient. I don't want to pick the endpoint. And anything between 6 and 10 would be sufficient. Again, don't want to pick the endpoints. So there's nothing special about those two values I picked other than they're in between the stuff that matters. And then I need to see what the derivative is doing. So I want to look at what g prime of 9 is going on there. Well, remember that g prime is the same as f of x. So this is the same thing as f of 9, which is like here or something. That's negative. And then g prime of 11, well, that's the same thing as f of 11. That's like here. That's negative. So what can I say if my graph goes from negative to negative? So it's going from decreasing, slope 0, back to decreasing. Right? This would be like what g would look like, or this is x equals 10. What is that? That's a neither, right? And our justification would be like what we've shown here, that we checked to see if 10 was a critical point, and then we did like a first derivative or second derivative test at 10 to see if it was a maximum, minimum, or mean. Again, this is like a first semester idea that we're applying on second semester concept. Feel okay? This is what makes the course hard, is now we're going to be continuing to layer this stuff on and take old ideas and use them in new settings. These first and second derivative tests are not going to go away. You're going to see them over and over again in second semester still. Okay. Part B says, does the graph of G have an inflection point at x equals 4? What does a inflection point mean? The concavity changes. What does that mean in terms of derivatives? The second derivative is going to change from positive or negative. Okay? Does that mean the second derivative has to equal 0 in between? Could be undefined too, right? So we go from negative to positive, or from positive to negative, right? Is that okay? And I know that the second derivative of g is the same as the first derivative of f. So I'm just going to do like one of these guys. So the second derivative of g double prime of 3 is equal to f prime of 3. So x equals 3 is here. So the slope of f at 3 is positive. And then we'll do the same thing now for 5. So 5 is there. The slope there is negative. So we would say then this is an inflection point because we have that change in concavity happening at. You okay?
Yeah, I'm fine.
Okay. Don't choke. All right. Should we do C? C says find the absolute minimum value and absolute maximum value of G on the interval, the closed interval, -4 to +12. Justify your answer. What are we going to need? Critical values and the endpoints. Excellent. So I need to take g prime of x equal to 0. That's the same thing as f of x equal to 0. So I have those answers from before, -2, +2, 6, and 10. Yep. And there were no other place where it was undefined, right? So I'm not going to bother writing that because we did up here already. Go get a drink? Yeah, of course. Mm-hmm. And then I need my endpoints. So those guys, right? So I'm going to compute then. Oops. Those values. Very good. Okay. So let's write it down. This is going from 2 to x. Everybody's good with that? What don't I like about that? Big to small. Let's flip it. Everybody okay with that? This is just the area under the curve from -4 to +2. So it's those areas, right? Is everybody okay with that? Well, you notice about these two. Cancel each other out, right? I have the same amount below that I do above. So I'm left with just that section. So this is width of, or base of 2, height of 4, and then divide by 2. So that's going to be 4, right? But I have this negative sign out front, so it'll be -4. Right? We picked up that negative when we flipped the bounds. Anthony?
Why isn't -2 a critical point? Why is it on -4 to -2?
Well, -4 was one of the endpoints. So I'm just plugging -4 in to x. Matthew. Go ahead. Is everybody, that works for you? Okay. Same idea. gonna do the same flippy floppy. This time we're going from -2 to +2. So we're looking at just this area. So base of 4, height of 4, that's 16, and then divided by 2 is 8. But remember we flip-flopped the bounds. So again, we picked up that negative sign. There's a lot of coughing and sneezing and those. Are you girls okay?
We're all infected.
Yeah. Guys need to stop sharing water bottles or something.
We're just coughing, Anthony. If I did this,
All right. G of 2, what's that equal? This was one you should be able to do in your head.
0.
0, very good. Why is it 0? Anybody but Anthony? Who I assume knows why it's 0 because he said 0. Why is it 0? What is the integral that G of 2 is? The integral from 2 to 2 of f of t dt. We know that the integral from a to a for any a is 0, right? Do you go get a drink? You have a drink in front of you. Maybe take a sip. Okay, let's do G of 6. Here we're going from 2 to 6. So we're looking at that area, which is positive 8. G of 10. So we're going in an area from 2 to 10. So those areas cancel out, so it's 0. And then to 12. So these two cancel out. This area is -4. Right? 2 times 4.
Is that the same as the first one?
Yes, it is the same as the first one. You could notice that that's the exact same triangle we drew in the first case. Yup. So, there's my absolute minimum, there's my absolute maximum. Okay? Okay. Who can tell me the intervals from -4 to 12 where g of x is negative?
-4 to 2.
Yes.
And then from 10 to 12.
Yes. So notice that the g of x is 0 at 2 and 10, right? It's a continuous function. Before 2 it's negative. After 2 it's positive. After 10 it's negative again. So we notice that it flips sign at 2 and 10, where it changes from negative to positive back to negative. But isn't it convenient how the work for one problem allows you to answer the next one almost without actually having to do anything if you just notice what you got? That's, again, common AP presentation where rather than this is a whole different problem, it's like, oh, I just used what I had from the previous and can build on that for the next one. I just have to interpret it or whatever. Yeah, it's a rough day. All right. What do you guys feel on this? Do you feel okay with what we've done? There's still some more here. I'm going to leave these for now. We'll circle back and we can do some more practice on this. I want to leave some for you guys to try at home also. So I don't want to burn through all of these, but they're all fairly similar where they're taking this, you know, accumulation function and using it to do first semester ideas on. In section 5.4, we're going to look at something called an indefinite integral. So recall in section 5.3, we defined the definite integral as the integral from a to b of f of x dx, which is just going to equal the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a, which boils down to just being a number. The indefinite integral is the integral from, notice there's no bounds here, that's how you know it's indefinite. It's just the integral of f of x dx, which is now, instead of a number, it is a function. That function is the general antiderivative for f. So if you can do the definite integral, you need the antiderivative to do that. You can do the indefinite integral. In fact, it's an easier process because there's no calculation at the end. You just find the antiderivative and you're done. Okay? So for example, the integral of x squared dx is x cubed over 3 plus c. And I know that's the antiderivative of x squared, because if I take the derivative of that, I get x squared back. So far, so good? So this table here is one that you should have memorized. This is all of our antiderivative rules that we've now recast as integral rules. But it's the same derivative rules you've seen, just packaged backwards. It's the same as the antiderivative rules we looked at 4.9. So this isn't new, this is just recast. Are these things you should have memorized? Yes. Should they be memorized like now? Yes. If you are still shaky on your derivative and antiderivative rules, you need to get on that sooner, like this weekend, make some flashcards, get reacquainted. At one point, you should have known these pretty well. If you're like, yeah, I was still kind of shaky on some of those, like you gotta clean that up sooner the better, okay? Like have to have them, they have to be fast. On the AP exam, there's not gonna be time to have to sit there and hum and haw about which one is it. You gotta know. And I would say very likely, maybe before the unit exam, we'll have a little quick, like, formula memorization quiz for like 10 points or something between, you know, the related rates and the unit test to give you guys a chance to like incentivize you to make sure you have these memorized and pick up some free memorization points. Everybody's okay? All right. So let's do a bunch of examples now. That's it for like idea. That's like the big idea. There's one more smaller idea here, but like that's the main idea for this lesson. It's just the antiderivative is the same as the indefinite integral. I should say the general antiderivative because you need the plus c. All right, so how do I do something like this? Well, I'd start by distributing the integral symbol across my function and then pulling the coefficients out front. So I'd have like 10 integral x to the fourth dx minus 2 integral secant squared x dx. Everybody okay with what I did there? Again, I feel like I can do that in one step with you guys because it's the same thing that we've been doing with derivatives all through first semester, right? We distribute it across, hold the coefficient to the front. What's the antiderivative of x to the fourth? X to the fifth over 5. Right, everybody remember? That's our formula here, right? Okay. And what's the antiderivative of secant squared? Tangent. And at the end I need a plus c. And that's it, I'm done.
Same time as algebra.
Notice that this is the same process that we did with 4-9 when we did antiderivatives, right? That was a weird noise. That's okay, I'm just making a comment. Let's look at this example. I have the integral of cosine theta over sine squared theta d theta. Do we know how to do the antiderivative of a quotient? So there must be a way then to rewrite what we have here as like one of these boys up here, right?
Distribute the integral.
No. Yeah, good question. No, definitely wrong. Very, very wrong. Just like we can't do that with a limit. So what we're going to do here is I would think about it as my insides is this. What's cosine over sine? Nope. Cotangent. And 1 over sine is cosecant. Oof, guys. Add this to your list of memorizings. Yes. Hi, Mary. Oh, cool. Thanks, dude.
Thanks.
We'll see you in a little bit.
You guys sit over there. Seriously.
Guys, I swear, I'm not thinking we're like, it's just the right one.
Get a look at this guy.
And then this, that guy right there. So I have negative cosecant. Again, remember, for memorization purposes, all the co-functions are the ones with the negatives. Cosine, cosecant, cotangent, those are all the ones with the negatives, whether you're doing the derivative or the antiderivative. So far, so good? Okay. How about this one? How's this different than the previous ones?
It has numbers.
It has numbers, so this is going to just equal a number, okay, not a function. Does the start change at all, though? Still find the antiderivative, right? Antiderivative of x cubed is? Okay, minus 6 times antiderivative of x squared over 2, and we're evaluating that from 0 to 3. So I just plug 3 in for x, and then I plug 0 in for x, and I subtract. And whatever that number is your answer. I'm not going to grind through the arithmetic, because it's just like kind of yucky looking, right? Yes, it's not that bad. right? Negative 81/4 or something, I think. No, well, it's like a fourth of 27 minus 1/4, so it should be 3/4 of 20, negative 3/4 of 27. Which I think is 81/4.
1/4 minus 27.
Yeah, I don't know, whatever. How about this boy? What do we notice? Well, it's still going to be a number, right? This is a definite integral. Anthony notices there's a fraction there. So again, if we think about this, we can do this stuff. Everybody's okay there? I just kind of distributed through and pulled the coefficients to the front. Antiderivative of x cubed is? Antiderivative of x is? Antiderivative of 1/x² plus 1 is? Tan inverse, yeah. And then evaluated from 0 to 3. So we're going to have 3 to the 4th over 2 minus 3 times 3 squared plus 3 times tan inverse 3 minus 0 to the 4th over 2 minus 3 times 0 squared. Oops, that's plus though now. And then minus 3 times tan inverse of 0. And then it's like arithmetic time, right? Can you do tan inverse of 3 without a calculator? I don't think so. Yeah, I don't think so. Is everybody okay with what we did? So if this was a no calculator problem, tan inverse 3 would be in your final answer as like an extra term. Tan inverse of 0 you can do with no calculator. What tan inverse of 0? Quick. No man, 0. You should be able to do this stuff in your head after a course in trigonometry and pre-calculus. I know, it's asking a lot sometimes. What about this guy? Again, I notice it's a definite integral, right? So the answer is just a number. But that function that I'm asked to integrate is a fraction. How am I going to deal with it? Yeah, good. So you can rewrite that as 3 fractions with a common denominator. Everybody's okay there? Which is nice because that's a heck of a lot easier to deal with. Oh, yes, it is -2. Thank you. So far, so good? So the antiderivative of 2 is? Well, t in this case, right? Because we're integrating with respect to t. But yeah, 2x is fine. And then the antiderivative of t to the 1/2 is? Okay, so that, right? And then antiderivative t to the negative 2. That guy, right? And then evaluated from 1 to 9. So I have to plug stuff in. You guys get the idea. So this stuff that we did today so far, this should be relatively easy, right? We're just doing antiderivatives again, and then maybe plugging some numbers in on our calculator and finding an answer, like having to do some whole number arithmetic and getting an answer. Not the worst thing I've ever done. Mostly the key is still having the derivative formulas from first semester memorized. If you are still solid there, this will go quite quickly. If you're not solid there, like have the list of antiderivatives out next to you and it'll go pretty quickly with it. Hopefully you'll start to memorize them as you go. Final idea for 5.4 is this idea of like net change being related to an integral. So if I think about this as like the integral of velocity with respect to time, right? The antiderivative of velocity is position, right? If I take position 2 and subtract it from position at time 2 minus position at time 1, what I have is the net change in position. Like how far apart is the thing at the start from the finish. Everybody agree? So this idea that an integral in a real world sense is going to represent like a net change is something we'll use fairly frequently. Let's look at a specific example. So it says a particle moves along a line so that its velocity at time t is v of t equals yada yada yada. Find the displacement of the particle during the time period 1 to 4. What does displacement mean? Just means like net change in position, right? So where are you at the end minus where are you at from the start? The difference in those two is your change in position. Everybody agree? So that is specifically then the integral from 1 to 4 of v of t dt. Everybody okay with that idea? No big deal. The antiderivative of t squared minus the antiderivative of t minus the antiderivative of 6, evaluated from 1 to 4, and you crunch through that number. Okay. Now, if I talk about distance traveled, what's the difference between distance traveled and net change in position? Let me illustrate it to you.
Displacement in total.
This is time 0. This is time 2. What's my net change in position? 0. How much distance did I travel? Yeah, 20 feet or something, right? Okay, so the total distance traveled, it will always be greater than or equal to your net change in position. When is it going to be equal? If you're only moving in one direction, you're always moving forward, your net change in position will equal your total distance traveled. But if at any point you change direction you're traveling, like you turn around and come back the way you came, you're going to have more distance traveled than you do change in position, right? So how am I going to, so this is going to be like forward distance plus backward distance, right? How am I going to do that for my integral? Like symbolically, what am I going to do there? Absolute value, right? If the velocity is always just the same sign, if it's all just positive, then that'll be the total distance traveled. What's the catch? Do you know how to do the antiderivative of an absolute value? Yeah, guess what? There isn't a formula for it. What are we going to do? Well, we're going to take that velocity function and we're going to set it equal to 0. We're going to find out where the velocity changes direction. So to solve this, I'm just going to factor it. Yes? Certainly. Now I'm going to draw a sign diagram and figure out where the velocity is negative and where it's positive. Or I should say when it's positive and when it's negative, since t is time. It's like a when question. So if I plug -3 in for t, I have negative times negative. If I plug 0 in, I have negative times positive. If I plug 4 in, that's positive times positive. Everybody's okay there? So specifically from 1 to 3, my velocity is negative. Everybody agree with that? So if I take the negative of that velocity, it would then be a positive velocity, right? That's like what I do when I take the absolute value of a negative number. So I make it negative on top of the negative and they cancel each other out. And then from 3 to 4, the velocity is positive, so I can just add that area. This one.
When you take when you find the zeros, couldn't you just throw out t equals -2 or t plus 2 and plug in values for t minus 2?
Yeah. I mean, I just did it generally because if it was, you could have had, if it was -5 in the middle, then you would have both 2 and 3 to worry about, right? So I just did it generally. But yes, in this particular case, you can say common sense dictates negative time does not matter, and you can throw that out of your sign diagram. That would be okay. The issue, though, is that you got to make sure that you still pick this value. Can't be like -10, right? It still would need to be in between -2 and 3. I don't think you'd be insane enough to pick that, but just throwing that out there. And then from here, it's like the same problem as above, right? You have the antiderivative already. You just, hard part is making sure you keep the negatives straight when you do plug the numbers in. Does that feel okay so far? So here we have a graph of power consumption where the y-axis is like the rate of power consumption and the x-axis, or the t-axis, I guess it's labeled, is like time in hours. We want to figure out the total amount of power consumed in a day. So again, we're looking at the integral from like 0 to 24 of like p of t dt. The y function is labeled as p. Everybody's okay with that idea? And that's really just the same thing as the area under the curve, right? How am I going to find that value from just what I'm given? I'm counting boxes here, right? Making an approximation. You know, I don't know, I got like this rectangle, and I got like that rectangle, and like this rectangle, and like that rectangle, and like that rectangle. So I can add up those areas, and then I'll just like approximate the little leftovers to the 10th of a box or whatever. I'm just counting boxes, basically. Does that feel okay? Now, I'm not going to actually do it for this one because there's like an annoyingly high number of boxes, like Yuckarooskies. On the AP exam, they would give you something with like 70 boxes or whatever they have to count. Like, that's just obnoxious. The same thing would be accomplished if, like, you know, you did this over like a 2-hour stretch or whatever, a 3-hour stretch, where you do the same kind of approximation or whatever. A lot less boxes to count. But that's the idea. What do you guys think? Is this okay? So that's like, that'll end us here for today. So we did 5.3, we did some application in 5.3, so we talked about that a little bit more. We did 5.4. We're done with both of those. Next time we'll do our related rates little mini test and finish up 5.5. And it'll be the following class will be like homework quiz-a-palooza. So we'd have like potentially 3 of them hitting that day, and then we'll just do a bunch of review stuff. Because we'll finish the content for the first unit, or the content that I want to cover in the first unit. And maybe we spend a little bit more time in 5.5. We'll just kind of play that out. 5.5's the first, where we learn like a new anti-differentiation technique that's not just like one of the derivative rules in reverse. So it'll be how to work the chain rule in reverse. It's kind of what the 5.5 is going to show us how to do. Which, although it's maybe the most difficult derivative rule to kind of get the hang of, it's the easiest antiderivative rule to get the hang of the product and quotient and chain. The chain is way easier to do the antiderivative of. The hardest is probably the quotient, because we never do that in general in the class. We just do like simple, well, not even simple, but we look at like specific techniques to deal with quotients of certain types. We never do the quotient rule in general in a like calc 1, 2, 3 type classroom. So it's always going to be like, oh, if it looks like this, we can do one of these guys to it. But we never handle it in generality. And the product rule in reverse will do, but is a BC topic. It'd be a normal Calc 2 topic, so we're going to do it. So I'll do a few selected BC topics. That'll be one of them, because it would be something you'd see in your first, like quarter of the semester of Calc 2. So I think it's worth doing, so you've seen it, do it. You get to that, if you're going to hang around that long to get there. Calc 2 is pretty common if you're doing anything technical, whether it's finance or medicine. Not uncommon to have a Calc 2 co-rec in your pre-med or finance degrees, and it seems like those are, in engineering it's a given. You can do all this crap for engineering for a long time. But those seem like the kind of the most common
end routes for the students in here, so I want to cover a good deal of that stuff. That doesn't isn't a wholly separate topic. Like there's BC stuff that we won't touch. You know, like we'll do no sequence and series stuff and no hyperbolic stuff and no parametric stuff. But those are like a separate topic. If we're gonna do integration, let's do all the integration stuff, even if there's like a stray BC topic in here. And I'll tell you before the test, like what are the BC topics or whatever. But we'll do some of those integration BC topics because I think it's appropriate to do it. We're doing it already. Might as well. So at least when you're in your second year calculus course, you're like still sitting here doing stuff I did in high school. You know, like that's usually a good thing. And you're happy that that happened. It's like, yep, I kind of remember doing this still. Or maybe not, like, this looks familiar, but oh boy, I was bad at it. But even then, it's like the second time around, how much easier are things, you know? Anyway, I don't know. That's it for today. How do you guys feel on this unit? Yeah, this should feel all right. We've kind of turned the corner, and things are starting to become like, oh, this reminds me now of the stuff we did in first semester that wasn't, you know, like it's hard, but not like hard, like make my brain hurt hard. Where it's like I struggle to understand what it is we're doing here hard. It's just like getting comfortable with the mechanics hard, which usually we're quicker at the pickup than the conceptual hard. The conceptual hard is just hard, like where you have to think deeply and understand what is actually happening and what the the machinery is doing behind the scenes to connect ideas together. That's hard. That's hard at any level, whenever you're doing it. That's the hard stuff like that. The actual like doing the procedures, well, that can be hard, but it's just like that's just practice hard, not like understanding hard. Practice is easy, understanding is hard. You know what I'm saying? So we've turned the like conceptual corner here, and I don't know that really that we get heavy conceptual again in second semester. So the next test is like all techniques, like more integration techniques, dumped a bunch of that. And I can't remember if there's an application stuck in there or not. I don't remember when we do volumes. If that's in this next test or the test after. I tend to think it's the test after, but you know, there's a little bit of integration technique left, and then application is like all we got left in here. So the heavy conceptual stuff is kind of in the past at this point, which is pretty cool, right? Like that's the stuff that's scary stuff. Where it's like, oh, this is cool, like you just took up like an entire sheet of paper with like crazy symbols here. Now it'll be an entire sheet of paper with symbols that make sense, at least, you know, or just like algebra symbols. It's like, oh, we had to do all this, do this integral, huh? All right. Like you guys did partial fraction decomposition last year in pre-calculus? No? You remember that? Where you want to take a rational function and rewrite it as the sum of rational functions with unit denominator or unit numerators? Oh, well, we'll have to. That'll take a little bit more time when we have to do that here. That's an integration technique to get around quotients, because some quotients are doable, some are not. What else is there? And then there's another trigonometry overlap, where depending on what the format of your rational function is, maybe making like a triangle and rewriting the problem as like a sine, cosine, tangent problem makes a lot of sense. It makes the problem doable. So like, we'll go back to like right triangle trigonometry as a means of making an integral that's doable for us using our normal anti-differentiation rules. And those are rough, just because of like the layers of stuff. It's easy to kind of get lost in the problem. If you're not real tight on your trigonometry, that could be a challenge. But it's basically like right triangle trigonometry ideas like sine, cosine, tangent, Pythagorean theorem. It's not so bad. What do you guys think? It's all right? No, I'm just talking about what's left to do. Volumes is usually the hardest thing left. Calculate the volumes of a regular shaped solid. Which is a common engineering problem, right? Like, I'm gonna build this part, it looks like this. How much stuff do I need to build it? It's like, okay, well, how would I compute this? Short of actually like building the part, like doing some water displacement or something, which is like only so accurate. That's what Archimedes did. You know the story of Archimedes? You know what Archimedes is? Yes? Ancient Greek inventor, mathematician. The city of Syracuse, I think is his, Syracuse is his hometown, I think. So like, the king of Syracuse orders a new crown to get made, right? And hires the jeweler in town, and the jeweler makes this crown, and the king's really happy. And then rumors start going about that the jeweler cheated the king. The crown isn't actually pure gold. It's just like gold plated, and it's like lead underneath or something. And the king's getting real mad about all these rumors. And he's like, I need to know, is this crown pure gold or not? And I love the crown, it's beautiful. I don't want to just like chop it in half and ruin it if it's real. But like, it's really bothering me that I don't know. So he enlists Archimedes to try to figure it out. Like, you can't destroy the crown, but I gotta figure out like, is this pure gold or not? So the question basically becomes like, Archimedes has to figure out the density of the crown, right? So what he does is he takes some gold equal to the weight of the crown, submerges it in water. Well, actually, that's not how it's sort of. It's like he racks his brain on this and can't figure it out. He's driving everybody nuts. Eventually, his wife's like, go take a bath, just relax, take your mind off the problem. And so he's like going in the bath, he sits down, and what happens when you sit down in the bath? The water rises, right? And he sees this and he's like, aha, eureka! And gets up, jumps up out of the bath and goes running off to his workshop, stark naked, screaming, eureka, I got it. That's the funny part of the story. So, looks at how much water the crown displaces, looks at how much water an equal weight of gold displaces. They don't displace the same amount. That demonstrates that the crown was a fake, that it's not pure gold all the way through. And the king kills the jeweler. End of the story. Anyway, Archimedes had a whole slew of ancient inventions. Had like a real clever way of like transporting water up elevation. He used like a screw where you turn the screw and it like, as it spins, it pulls the water up. So that was something that was easy to automate, like you just get an animal to walk in a circle or whatever and it turns the screw and you can like now bring water to the second floor of your house or whatever without having to carry the water up the hill, which stinks, or carry the water up floors or whatever. And a bunch of war inventions. So like at the end of his life, Rome is conquering Syracuse or whatever. And like Archimedes is the prize, it's the reason to conquer Syracuse is you want to capture Archimedes and have him make weapons for you. So like the Roman soldiers sent in to go capture him or whatever, and he's in his workroom doing like some calculation on the floor, and the soldiers come in, they're like, "You're coming with us." He's like, "Shut up, I'm in the middle of this." And they're trying to drag him out of there, and he's like refusing to go. Impatient soldier runs him through, that's the end of his life. But like, had a bunch of like siege inventions, like one that was like, would pop up out of the water and like grab a ship and like tip it over. Like this stuff worked, had like a death ray, like a way of focusing the sun's energy and like setting boats on fire. Like really like a generational talent. Anyway, I don't know, that's our Archimedes for you. See you later, guys. Another great day of story time with Mr. Bullock, where I tell you about like some weird story you never thought you'd need to know.